Okay, so let's review some of the material from the applications of derivatives, and we'll start here with absolute and relative extrema. So if we look at this graph here, let's try and identify any absolute and relative extrema. All right, so let's talk absolute first. All right, well, it looks like here we have an absolute max as the very highest point in that region, in this whole function here. So on the other end, notice that it's open at what would appear to be the absolute min. So there is no absolute min here. And then inside here, we have a couple of places where it bottoms out temporarily and tops out temporarily. So here, we're seeing a relative min, and here, we're seeing a relative max. All right, and notice that the relative min occurs at a place where the derivative is 0, and the relative max occurs at a place where the derivative is undefined. And that's a good example of why we look to those places when we're doing an analysis of a function to look for relative extrema. All right, so to summarize, we had an absolute max at x equals 1, absolute min, none, and a relative max at x equals 3, and a relative min at x equals 2. Okay, so now let's find the absolute extrema of this function. Now notice the previous function by the graph did not have both an absolute max and min, but if we take a continuous function on a closed interval, which that was not, we will have a guarantee of an absolute max and absolute min, so that's what we have here. Okay, so again, if we're going to do this, remember the basic idea. The absolute extrema are going to occur at one of two places, either at critical points inside the region or at the endpoints. So we're going to have to find those and check them. All right, so our f of x here, so I'm actually going to multiply this out in order to take the derivative. So 4x to the 3/5 minus x, so x to the 3/5 times x is 5/5, so that's a total of 8/5 there. All right, so when I take the derivative, this one's going to be a little messy. So what do we get? We're going to get 12/5 x to the minus 2/5 minus 8/5 x to the 3/5. Okay, that's an 8 there. And if I were to factor this, I could take out a 4/5, and I would have 3, and I'll put the x to the 2/5 in the denominator, minus 2x to the 3/5. Okay, so that looks like it's pretty good to work with. All right, so now I ask my two questions. When is the derivative equal to 0? When is the derivative undefined? When the original function was defined. All right, so let's start here. If the derivative is going to be 0, then I would need this in here to be 0. So I would need 3 over x to the 2/5 equal to 2x to the 3/5. If I cross multiply there, I would get 3 equals 2x. So if I multiply x to the 2/5 and x to the 3/5, I get x to the 5/5 or 1. And so I actually get x equals 3/2. All right, so that's our critical point. We also have, that's a critical point. Now let's look where the derivative is undefined. Okay, notice the derivative is undefined when x is 0 because I got this x to the 2/5 in the denominator now. And originally, it was defined at 0. So this is a critical number that we need to consider. All right, so what's next? Well, I'm going to take my original function, and this time I'll write it in the original way. All right, and now I'm going to evaluate it at all the endpoints and critical numbers in the interval. All right, so the end, so it was -1. I had 0, I had 3/2, and I had 4. These were endpoints, and these were critical numbers inside the interval. All right, so I go ahead and evaluate these from the original function. All right, so I get -1 to the 3/5 times 4 minus -1. That's a -1, so -1, 5th root is -1, cubed -1 times 5, so -5. 0 is going to be 0 times 4, so equals 0. This one is not going to be a nice number. We would need to use some type of calculator to get this, because 3/2 to the 3/5 is not going to come out nicely. But if you use some sort of calculator, you find that this is approximately 3.19. And 4 to the 3/5 is not nice, but then we also have 4 minus 4 here, which is 0, so this ends up being 0. So now all we do is we go to the problem, and we go to the values that we have. Our biggest, there's our absolute max at f of 3/2 is approximately 3.19. So that 3.19 is actually our absolute max. And there's our absolute min. F of -1 is -5. So -5 is our absolute min. Okay, let's take a look now at a mean value problem. So determine if the mean value theorem can be applied. If so, find the value or values guaranteed by the theorem. All right, so here's our function. There's our interval. Remember, we have to ask two questions. Is f of x continuous on the closed interval? And is f of x differentiable on the open interval 0, 1? If these are true, then the MV2 will apply, and it'll allow us to guarantee that the derivative will take some values, certain values. Okay, so let's look. Is it continuous? Yes, both of these functions are continuous, certainly on that interval, but everywhere in the real numbers, where they're defined. Square roots are not defined in the negatives, but everywhere from 0 onward. Is it differentiable? Let's take a look at the derivative. 1/2 x to the minus 1/2 minus 3/2 x to the 1/2. Or in other words, that would be 1/2. Well, I could factor out a 1/2, make this a little nicer. 1/2, and then 1 over the square root of x, because it's 1 over x to the 1/2, minus 3 square root of x, just to look at it a little nicer. Okay, so what we see is that yes, there is an issue at x equals 0, but meaning that it's not differentiable at x equals 0, but we only need it differentiable on the open interval 0, 1. So it is on the open interval differentiable. Okay, so all this means that MVT applies. So that means we can go ahead and proceed. So that means there's going to be a guaranteed value of the derivative, f prime of c, which is going to be f of b minus f of a over b minus a, which is going to be f of 1 minus f of 0 over 1 minus 0. Now, there's the function f. If I plug in 1, I'm going to get 1 minus 1, or 0. And if I plug in 0, I'm going to get 0 minus 0, which is 0. So I'm actually going to get 0 minus 0 over 1, 0. So, in fact, our guaranteed value of the derivative is 0. So this is actually the special case of rolls, but that's okay. Doesn't matter. We can still just think of it as mean value theorem. All right. So where does that happen? In other words, what is our c, or what are our c values? Well, in that case, we just take the derivative that we had, which was 1/2 1 over the square root of x minus 3 the square root of times square root of x, set it equal to this guaranteed value of 0. That would mean that the stuff inside here, 1 over the square root of x minus 3 square root of x, would have to be 0. 1 over the square root of x equals 3 square root of x. But if we cross multiply there, we see that we would get 1 equals 3x when the radical x's multiply. In other words, x is 1/3. And if this worked out, since we only got one value, it should be on the interval. And indeed, it is in this interval. So that is the c value that we were guaranteed. So there we go. We were able to apply the mean value theorem because we did the check. We got the guaranteed value of the derivative to be 0, and we were able to find out that that occurs at the c of 1/3.